A warm welcome to all the viewers for the course Advanced Manufacturing Technology, and myself Thiapal, Assistant Professor of Department of Mechanical Engineering. Today I am going to give an introduction lecture about electrochemical machining process. So before we start with the electrochemical machining process, we have already gone through various non-traditional machining process. And the most important thing is that every time we would like to know that why we are preferring the non-traditional machining. As because there are few processes which can be implemented to get the desired complex shape product which cannot be performed by normal conventional machining process. Obviously, the workpiece has to be electrical conductivity so that we can carry out the process. So this is another process, that is the electrochemical machining process, where through the chemical reaction we are going to perform the machining. In fact, in other words, we can say that electrochemical machining process is just opposite of galvanizing or some sort of deposition process. So hope you will get a brief introduction in this particular lecture, where we will be basically deciding or discussing about the working principle of electrochemical machining process. So now let's have a look for the next portion, that is what is the content of this particular lecture. So what is the content? You can see here, that is Introduction of electrochemical machining, working principle, mechanics of material removal, electrochemical machining setup, process parameters, applications, advantages and disadvantages, and then at last we'll be having little bit a quiz test, which is very simple but very interesting. So now let's move to the next portion. So now we are coming for the introduction of electrochemical machining. Basically, electrochemical machining is one of the most potential unconventional machining processes. Though it is a new process for metal working, but the basic principle had been well known for a long time. This process may be considered as the reverse of electroplating with some modification. Further, it is based on the principle of electrolysis also. Basically, in a metal, electricity is conducted by the free electrons, but it has been stabilized that in an electrolyte, the condition of electricity is achieved through the movement of ions. Thus, the following of current through an electrolyte is always accompanied by the movement of matter. Now, the electrolysis principle has been in use for long for electroplating, where the objective is to deposit metal on the workpiece. But since in electrochemical, the machining, the objective is to remove material from the metal or the workpiece which is connected to the positive, and obviously the tool is always connected to negative terminal. Now ECM, as I've already told, it is a recent and most useful machining process. Obviously it is a non-conventional machining system in which the material is removed by electrochemical processes. Next, as I've already told, it is reverse of electroplating. Means it removes your metal instead of adding it. Basically, it is used for mass production purpose and also used for hard materials that are very difficult to machine using the conventional process. Both external and internal geometries can be machined with this particular process. Now, we were talking about the electrochemical machining. As you know, this is a very important or most potential unconventional machining process. Though it is new for metal working, but the basic principle is always known for a long time. And the most important thing is that the process may be considered the reverse of your electroplating. And some modification has been also added to it. Further, the principle is basically based on electrolysis process. And I think electrolysis process is known to all of us for a long time ago. Now, in electrochemical material removal, an electric field in an electrolyte destroys the atomic bond of the material. Now, let's have a brief look at the history and the early development that has been performed for electrochemical machining process. So if I go for the year in 1929, then experimental electrochemical machining process was developed by W. Gussif. So in the year 1929, electrochemical machining was first introduced by W. Gussif. Next, in the year 1959, commercial process was generated by the Anukat Engineering Company. So the process was invented. After that, its commercial process was basically generated by the Anukat Engineering Company. Now in the year of 1960s and 1970s, gas turbine industry was introduced, and where this process was been used for several times. Next, later, with the passage of time, rise of electrodischarge machining in the same period slowed down the electrochemical machining research. With the advancement of technology, the demand of some non-traditional process has been slowed down because electrodischarge machining is much more advanced process than your electrochemical machining with respect to research area. Now, original problems of poor dimensional accuracy and environmental pollution waste. In ECM, the original problem was associated was poor dimensional accuracy, and your environmental polluting waste was generating in a high amount. So to avoid this particular thing, the new process raised, and that is electrodischarge machining, and with the increasing or raise in demand for EDM decreased the demand for ECM in the history of non-traditional machining. Now you can see that this is a basic symmetric diagram for electrochemical machining, and you can see this is basically your tool electrode, and it is connected towards negative terminal, as you can see here, and this is your workpiece which is connected to positive terminal. Okay, now if I go through this particular picture, then very basic principle has been explained here. That is, in this particular figure, it shows a workpiece. A suitable shaped tool has been used, and the gap between the tool and the workpiece being filled with suitable electrolyte. So what I am telling, this is your tool electrode, this is your workpiece, this is the gap you can see, and basically this gap is totally filled with suitable electrolyte. Now when you pass the current Again I am repeating, when you pass the current or when the current is passed, the dissolution of the anode occur. Again I am repeating, when the current is passed or when you are passing the current, the dissolution of the anode occurs. However, the dissolution rate is more where the gap is less. So you can say the gap is very less in this particular condition, and if the gap is less, then the dissolution rate will be more. Again I am repeating, if the gap is less, then dissolution rate, dissolution, dissolution rate will be more. But if I consider the same condition in the vice versa, that means for this condition, the gap is more. So dissolution rate, here you can see gap is more. So your dissolution rate will be less. And here what you can see, dissolution rate is more because your gap is less. So you can see how it is affecting. The gap is one of the important thing that it has to be maintained while machining. That is the gap between the tool and your workpiece. If the gap is less, the dissolution rate will be more. If the gap is more, the dissolution rate is less. Next, if the dissolution rate is less, then what it will happen? When the gap is less, the dissolution rate is more, and vice versa. Now, the current density is inversely proportional to the gap. The current density is inversely proportional to the gap. That means if your gap is more, your current density will be less. And if your gap is less, then your current density will be more. So again, there is a relationship between current density which is inversely proportional to the gap. So this is another thing that you have to remember, that is current density. Current density is inversely proportional to the gap. So you have to remember this one also, that current density is inversely proportional to the gap. Now, if the tool is given downward motion, as you can see, the tool has been given a downward motion. You can see the tool has been given a downward motion. The work surface tends to take the same shape as that of the tool. So you can see this is the particular shape of your tool. And you can see the shape that is generated in the workpiece is also same. So when you are inserting the tool over the workpiece, it is gaining the shape as that of your workpiece. I mean to say, as that of your tool, you are getting the shape over the workpiece. And at a steady state, the gap is uniform. You can see the gap is basically uniform, isn't it? So this gap is also maintained uniform, as you are able to see in this particular figure. Thus, the shape of the tool is reproduced in the job. So you can see this is the tool, this is the flat surface of the workpiece. But gradually when you are inserting the tool over the workpiece, it is gaining the shape of that particular tool. In an electrochemical machining process, the tool is provided with a constant feed motion. So what I was talking, the feed motion has to be constant. Feed motion that has to be constant. Okay, so again I am repeating, that is, in an electrochemical machining process, the tool is provided with a constant feed motion and the electrolyte is pumped at a very high pressure through the tool and the small gap between the tool and the workpiece. So now let's have a look for this particular figure. So this is the basic working principle of electrochemical machining, and you can say this is your tool. This is your tool. Okay, and this is the constant feed motion that I was talking. The tool has given a constant feed motion, and you can see this is the portion through which the electrolyte has been inserted, and this has been done. Insulation has been obviously done. This is the positive terminal, this is your negative terminal. Positive terminal is connected to workpiece, negative terminal is connected to the tool, and low voltage high current DC supply has been provided. And you can see this is the portion where you have got the splash electrolyte. This is getting ejected here. This is the tool, this is the workpiece. Electrolyte is flowing and it has been inserted at a constant feed motion. And you can see the electrolyte is pumped. The electrolyte basically it is pumped at a high pressure through the tool and the gap between the tool and the workpiece. The electrolyte is so chosen that the anode is dissolved, but no deposition take place on cathode. I mean to say on the tool. Again I am repeating. Have a very clear look at this particular point. The electrolyte is so chosen that the anode is dissolved. I mean to say anode means your workpiece is getting dissolved, but no deposition takes place on the cathode. I mean to say over the tool. Now the order of the current and voltage are a few thousand ampere. You have to maintain some order for current also and for voltage also. So if I have a look for current, you are going to use few thousand amperes, and if I talk about the voltage, then basically you have to choose the voltage between 8 to 20 volt. 8 to 20 volt you have to choose. Next, the gap is of the order. You are maintaining a certain gap, isn't it? You can see this is a certain gap has been there. Then what should be the distance of the gap? So gap distance that has to be measured between 0.1 to 0.2 millimeter. So you have to maintain a gap between 0.1 to 0.2 millimeter. In a typical machine, the material removal rate is about, if I talk about the material removal rate, that is MRR, it is none other than 1600 millimeter cube per minute. So in a minute you can see 1600 millimeter cube material is removed per minute. And what should be the current that they are using? It is always 1000 ampere. It is used 1000 ampere. Approximately 3 kilowatt hour are needed. Approximately 3 kilowatt hour are needed for removal of material, that is 16,000 millimeter cube of metal, which is almost 30 times the energy required in a conventional machining process. So 3 kilowatt hour is required to remove 16,000 millimeter cube of metal, which is almost 30 times the energy required in conventional machining process. Of course, when the metal is readily machinable. But with electrochemical machining, the rate of metal removal is independent of the workpiece hardness. Again, I am repeating, in electrochemical machining, the rate of metal removal is independent of the workpiece hardness. So, ECM becomes advantageous when either the work material possesses a very low machinability or the shape to be machined is complicated. Again, I am repeating, ECM becomes advantageous with work material process, a very low machinability, or the shape to be machined is complicated. Now, unlike most of other conventional and non-conventional processes, there is particularly no toolware for electrochemical machining. As I've already told you that no deposition is occurring at the cathode. It means no deposition is occurring at the tool. And if no deposition is also occurring, no tool wear is also occurring in this particular process. Though it appears that since machining is done electrochemically, the tool experiences no force. And this is the fact that the tool and the work are subjected to very large forces which is exerted by high pressure fluid in the gap. When you are ejecting a high pressure fluid in the gap, then only a large force has been exerted or it is subjected over the tool and the workpiece. Otherwise, the tool is not subjected to any sort of forces. So now, after having the entire working principle that I have already explained with the help of diagram, we are going to just discuss few things that we cannot overlook for the electrochemical machining process. So let's have a look. Basically, the working principle, it follows Faraday's laws of electrolysis. Again, I am repeating, electrochemical machining process, its working principle basically follows Faraday's law of electrolysis. So now let's have a look what Faraday laws of electrolysis basically state. The weight of the substance produced during the electrolysis process is directly proportional to number 1, the current which passes, number 2, the length of time of the process, and number 3, the equivalent weight of the material. So Faraday has been told, the Faraday law of electrolysis describes that the weight of the substance basically produced during the electrolysis process is directly proportional to the current which passes, the length of time of process, and the equivalent weight of the material. Now, Two dissimilar metals are in contact with an electrolyte and anode, lost metal to cathode. If you are preferring for two dissimilar material and they are connected with an electrolyte, then basically anode, that is your workpiece, lose metal to cathode, and cathode is always your tool. Now you can see this is another figure. It has been stating the basic material removal of this particular working principle. So you can see this is your workpiece, which is denoted as anode, and this is the cathode electrode. This is basically your tool. This is your basically tool, and you can see there is a current density, and it has, I have already told that current density having a relation inversely proportional to the gap. If your gap is more, the current density, if the gap is more, current density will be less. If your gap is less, your current density will be more. So you have to remember this particular relation. And you can see this is the tool, this is a gap there is present, and this is basically filled with electrolyte. Later on you can see this tool has been inserted over the workpiece to gain the shape of that particular tool. So now we are coming to a basic formula according to the Faraday law of electrolysis. If M is represented at weight of material in gram and I is represented as current, which is in ampere, and if T is represented for the time in second, then this eta, that is the gram equivalent weight of the material, and F is been denoted by constant of proportionality, that is the Faraday, that is 96,500 coulombs. Then what is the weight of the material? That is M is always represented by I into T into eta by F. So hope you will be able to calculate the weight of a material during the machining. Now this is another scheme principle of electrochemical machining, as you can see. Workpiece, isn't it? It is your anode. Tool, it is your cathode. So you can see this is workpiece, this is tool, and this has been a chamber which has been filled with electrolyte in this condition also, here also. Now just have a look here. If the gapping is more, initial stage, the gapping is more, and slowly when you are pushing the tool towards the workpiece, you can see it is gaining the shape of the tool over the workpiece, isn't it? And what we have taken here, anode we are always taken as workpiece, cathode as your tool, and electrolyte is an electrical conductivity fluid. Obviously the electrolyte has to be electrically conductivity of fluid, then only the process will occur, otherwise it is not possible. So again I am repeating with this particular diagram. All of you have a look here. Workpiece, that is your anode, tool is your cathode, and in the initial state, this is the initial stage and this is the steady state. So initial stage, what you are doing is that you are slowly inserting over the workpiece, and you can see here the material removal is occurring in the workpiece, but the material is not getting deposited over the tool. And the most important thing is that this tool is getting the shape over the workpiece. So the shape you want in the workpiece, it can be achieved by the shape of the tool that you are selecting. And the most important thing is that electrolyte, it should be an electrically conductivity fluid. Now we are having a brief look at the process. What the process it is showing, that is during electrochemical machining process, there will be a reaction occurring at the electrode, that is at the anode or it is workpiece, and of course at the cathode or the tool, along with the following reaction. So you can see what are the possible reactions that are occurring at the cathode and what are the possible reaction that is occurring at the anode. So if I go for the cathode, you can see. So we are going to have a look for the following reaction which is possible at the cathode. Okay, so cathode means at the tool. So what is the reaction you can see? Na plus electron minus, it gives you Na. Next, Na plus H2O, that gives NaOH plus hydrogen H, you can see here, H plus. Now this 2H positive plus 2 electron negative, that helps to get hydrogen evolution. And the most important thing is that the following reaction occurs at anode, that is the iron workpiece, that is Fe, that is gives Fe plus plus and 2 electron minus. And when this Fe plus plus get combined with 2Cl, it gives you FeCl2. And next you can see Fe plus 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 2OH, that gives you FeOH2. And last, that is FeCl2 plus 2OH, that gives you FeOH2 plus 2Cl minus. So these are the reactions that are basically occurring at the cathode, and these are the basically reactions that are occurring at the anode. So you just have a look here. This is the representation of electrochemical reaction. This electrochemical machining process is occurring due to this electrochemical reaction. So this reaction you are able to see here. This is the workpiece which is of iron, and this is the tool, and you can see in between them there is a gapping, and this is totally filled with electrolyte. So in electrolyte, what you are able to see, Fe plus plus, OH minus, then you can see H plus, Na plus. So all this thing you are able to see here. So this Fe plus plus and this chlorine, they get combined into FeCl2. And here you can see what you are able to get, that is FeOH2. So finally, this is the end of the first part of electrochemical machining process. So what we have already discussed, it is all about the general introduction of your electrochemical machining process. So if I describe it in a briefly manner, then what can I say is that electrochemical machining is obviously one of the most potential unconventional machining processes. Though it is very new process for metalworking, but the basic principle was known to all of us for a long time. And what important thing is that this process may be considered at the reverse of your electroplating with some modification. And the most important thing is that it is basically based on the principle of Faraday law of electrolysis. And in a metal, electricity is conducted by the free electron, but it has been established that in an electrolyte, the conduction of the electricity is achieved through the movement of ion. And what we have also discussed in this particular lecture about the tool, whatever shape you want to obtain over the workpiece, you have to be very sure while selecting your tool. Because the tool, the shape that you are selecting, it will be totally impinged over your workpiece when you are forcing it to be gated over that particular portion. And electrochemical machining, it's a non-traditional machining process, and obviously it is belonging to electrochemical category. As we have already discussed, non-traditional machining has got several categories. One is the mechanical category, one is the electrochemical category, another you have got some EDM, that is the heat generation. And in the mechanical category, we have already discussed about abrasive water jet machining, abrasive machining, ultrasonic machining. So today, in this particular lecture, we have covered up what is electrochemical machining process is. What is the basic history behind the mechanical history, or you can say that how it was invented, when it was invented, and by whom it was invented. And later it was followed by the thing that has been upgraded in the non-conventional machining, and then we are able to know about the electric discharge machining process also. So this is basically the lecture of electrochemical machining part 1, where we have just basically described you about the working principle. So in my next lecture, that is electrochemical machining lecture 2, we are going to discuss about all the materials or all the parts or the equipments that are associated with your electrochemical machining process. We are also going to discuss about the effect of this particular material or the parameters over your machining process. We are also going to describe about various advantages, various disadvantages of this electrochemical machining process. And of course, we are going to discuss about the applications that has been included for various sections. Hope from this particular lecture, it is clear to all of you what is electrochemical machining process is. And the most important thing is that, as I've already told you, electrochemical machining is opposite of electrochemical or anodic dissolution at atomic level. Okay, and of course it is also opposite of Galvan's coating or deposition process. And next is ECM can thought to be controlled by anodic dissolution at atomic level of the workpiece, and that is electrically conducted by a shape tool due to the flow of high current at relatively low potential difference through an electrolyte, which is quite often water-based neutral salt solution. So guys, if I just have a look for that what is the objective for going with the electrochemical machining, or what is the objective of this particular study, then first it is to identify electrochemical machining as a particular type of non-traditional machining process. Every subject has got some objective, isn't it? So what is the objective that we are following for this particular lecture? It is obviously our identification of electrochemical machining. Next, the basic working principle of ECM process that we have already covered up. Next is we have talked about the schematic diagram of electrochemical machining. Then we have also talked about the tool potential drop little bit way, but in the next lecture we will be going through this particular portion at the first. Then it will be followed by the material removal mechanism. We have to identify what are the process parameters that is associated with electrochemical machining process. Then there is a model for material removal rate. Again, we have to analyze the dynamic of electrochemical machining process. We have to identify the different modules of electrochemical machining equipments. And then last but not the least, we are going to talk about the applications, because every process why we are using, it has got some application, isn't it? So we have to be very sure about the applications. In my next lecture, I'm going to discuss about it. And the most important thing is that every process has got some advantages as well as disadvantages. So we'll have a brief look on the advantages and disadvantages also. So thank you guys for listening my video. Please stay connected with me so that in the next lecture you can get the overview of all this particular process that I have discussed here. And thanks for listening my video as well as having a look at the video. So please stay connected. If you have liked the video, then please like it and subscribe my channel to get more updated. Thank you.